Welcome back. Today is lecture 52 and we will continue our discussion on the matrices that we introduced in the last lecture on our module for microwave engineering concepts for devices. Okay, so to the whiteboard here. So I told you that we have different matrices. Here I am showing you the Z and the Y matrices. So, but again this is for an N port network. In a real life, in a not, I will not say real life, I would say in a practical situation of a transistor, which is what the focus of this course has been, we have just 2 port. Okay, so we do not have to consider up to N, we just have to consider 2, which is V1, V2. Okay, that is the input voltage, the output voltage is the Z parameter, the impedance matrix into the input current, the output current. So this will be Z11, Z12, Z21 and Z22. These are the different Z parameters. This is the impedance matrix. Okay. So of course you can say that V1 is equal to Z11 into I1 plus Z12 into I2. Okay, Z1 into I2. So now for instance if I want to find out the value of Z11, then I can say that Z11 is equal to V1 by I1 when I2 is equal to 0. If I keep I2 equal to 0, then Z11 equal to V1 by I1. So if I look at the 2 port, so this is your input and this is your output, correct. So this is your the plus minus, this is a V1 on the port here, this is V2 at the port there plus minus, and this is your current I1, this is your current I2 here. Okay. So if I say I2 equal to 0, which means I2 is 0, it means this is open. If I keep the output port open, alright, if I keep the output port open, I measure the input voltage by the input current, that ratio will give me Z11. So other parameter like Z12 and Z21, Z22 etc. also can be found out by either open, keeping one terminal open, or short as the case may be. Okay. For instance if I want to find out, so now if I look at this equation again, maybe I will remove the annotation. Okay. So for instance you have V1, V2 and then you have Z11, Z12, Z21, Z22 and this is your I1, I2. Okay. So you can also write V2 as equal to Z21 into I1 plus Z22 into I2. Okay. So if I want to write Z21 for instance, that will be V2 by I1 when I2 equal to 0. Okay. So it seems that we have to keep a particular port open, or particular the output port open or the input port open to get different parameters. That is one way of finding the Z parameters. This is the impedance matrix. But in certain cases you might want to go in an admittance matrix. Y matrix is the admittance matrix. Why? Because connections, there may be parallel connection. Okay, when you have parallel connection, life becomes easier when you talk about admittance Y instead of a pair, because in admittance, if you talk about admittance, then things in parallel will add in like a series. You can add Y1 plus Y2 etc. right, if you have admittances. But if you have impedances here, then you have to do a parallel which is more complicated. That is why you need an admittance matrix. Now if you have an admittance matrix, okay, now if you have an admittance matrix, for instance now I am talking about I1, I2 will be equal to Y11, Y12, Y21, sorry, Y22 and that is your V1 and V2. Okay. So suppose I now write down I1 equal to Y11 into V1 plus Y2 or Y12 into V2. Now if I want to find out Y11, the parameter, it is basically I1 by V1 when V2 equal to 0. What does V2 equal to 0 mean? V2 equal to 0 means that the output is short. This is your terminal, this is output, the output is short circuit. If I make it short circuit, then the ratio of the input current by input voltage will give me Y11. So again let's just I am pausing here. The Y matrix, this and the Z matrix that I talked about, physically they are talking about these parameters that relate the input and output voltages and currents. These are the parameters that are relating them, and if you go one step beyond and physically you are talking about, then some of these parameters, for instance one of these parameters could represent kind of the gain, one of them could represent the reflection and things like that, okay, the reverse gain and things like that. So, these are the parameters that are relating the output and the input parameters, the voltages and currents, okay. Anyway, so what we saw from this Z matrix and the Y matrix is that by keeping an appropriate terminal short or keeping an appropriate terminal open, you are able to measure you can measure the ratio of current voltage, voltage current, etc. to find out different Y parameter or Z parameter, Y11, Z11, Y12, Z12, etc. Okay, you can do that. But there is a practical problem here. Okay, when you, this is all good mathematically, but when you want to measure it experimentally, there are some practical problems. One of the practical problem is that we are talking about RF signal, electromagnetic signals. It is extremely difficult to maintain an RF short or an open in a real device across a range of frequency, because see, these parameters will keep varying as a function of frequency and you need to measure or understand this with respect to frequency. So, over a range of frequency, maintaining an RF short or an RF open is an extremely complicated task. It is very, very difficult, okay. That is one of the issues. And when you do this RF short and RF open, oftentimes the device can become unstable. It can start oscillating, it can damage the device, there can be instabilities in the device. So, practically keeping a port open or short across RF frequency is not something that can be easily done, that is very, very difficult, okay. I did not talk about ABCD parameter, I will come to that in a subsequent slide, but think of it as something similar. So, Y and Z parameter, they have a problem is that you cannot define an RF open or short over a range of frequency, okay, and they will become, the device will become unstable as I told you when you try to have this open and short at RF frequencies, okay. And another problem is that you cannot accurately measure the voltage and current, okay, when you have this you try to have this 2-port network with open short and you are trying to measure the Z parameter and the Y parameter so that you can understand the device or the network, it becomes very difficult to accurately measure them, keep them open and short for a range of frequency, the device will become unstable, and multi-port devices cannot be. If you have more than 2 port, it is not a transistor but something else. Sometimes you might have a mixer, for instance, and other oscillators, couplers, not couplers, circulators, they can have more than 2 port and then it becomes even more difficult. So, the best thing is to treat the incident wave, say V1 plus, and then the reflected wave V1 minus on the input side. Similarly, on the output side V2 plus and V2 minus, the incident and the reflected, the current also similarly. So, when you have this incident and the reflected, we talk about S parameter or scattering parameter. These are more practical to measure. Why? Because you do not need a RF open or short. You do not need an RF open or short to measure the S parameter. So, just like Z11, Y11, Z12, Y12, you also have S11, S12, S22, S21, S22. These S parameters do not require an RF short or an RF open, and it does not lead to any instability in the system or on the network, okay. Practically you can measure them. What you are doing is that you are talking about an incoming wave, reflected wave on the input side and on the output side, and you can actually measure that incoming power in a way. You can say the power that you are feeding in, you can measure from an instrument, and the instrument that is used to measure this S parameter is called a VNA, a vector network analyzer, okay. And a vector network analyzer does precisely that. Is basically that when you want to measure a parameter, say S11 or whatever, S21, etc., you do not have to keep another terminal open or closed or short. What you do is that you match the other port. So, you have a transistor, you have 2 ports, there is an input port, there is an output port. You want to measure S11 for instance, you do not have to keep the output port open or short, you have to match the output port. So, the VNA does precisely that, it matches the output port or the port of interest, it matches it so that there is no reflection, and that is enough. That is enough for you to measure S11 for instance or any of the S parameter. So, it is more pragmatic, you bypass these problems of Z and Y parameter and ABCD parameter for instance, okay. So, I will come to this example of Z parameter later maybe and ABCD also, but I am talking about S parameter here. So, here you see in a 2-port network, I will not talk about an N-port network, a 2-port network you have input side reflected, you have output side reflected is your S parameter, which is your S11, S12, S21 and S22 into the input side incident wave, the output side incident wave. You see, and this is the generic formula, but I can do it step by step. For instance, V1 minus is equal to S11 V1 plus S12 into V2 plus. Okay. So, what does it mean? It means that if I want to measure S11, then this is SV1 minus by V1 plus, while this is 0, V2 plus is 0. What does V2 plus equal to 0 mean? So, you have a transistor, this is the output port, this is the input port, correct, this is V1 plus and there will be V1 minus that is coming in. So, V2 plus, which you can see is the incident wave here, is 0. It means that this port is matched. If this port is matched, then the power will be transmitted, but it will not reflect from a load back to the device. So, V2 plus equal to 0 means that your load is perfectly matched. So, the VNA, the vector network analyzer, is going to match the load, match the output port, okay, so that V2 plus is 0. You do not have to define an RF short or an open, and the ratio of the reflected wave on the input side here to the incident wave on the input side, which you can measure very well, how much you are sending in and how much you are getting reflected back, you can measure in the VNA. That ratio will give you S11, and this is for a certain frequency, and as you change the frequency you will get S11 across a range of frequencies. Similarly, you can find S21, S22, S12, etc. Okay. S21 for instance is like the gain, how much gain you have from input to the output side, okay, and S11 is like the reflection, of course, on the input side. S22 is the reflection on the output side, S12 is the gain from the reverse side, from the output to the input, how much gain you are having in a way, okay. That will also be important for feedback later on, but anyways, this is the basic premise or the genesis of the S parameter, okay. You do not have to make any RF open short, you just have to match the port of interest appropriately, and when you measure how much power you are sending in or how much power is reflected, it is more reliable, you can measure it more pragmatically, and this is done by a vector network analyzer. So, maybe I will remove this so that you can read the code here. I mean, whatever I spoke is whatever is written here, which is you have to match the other port, one of the two ports. So, S11 just I discussed it in the last slide, right. The S11 is the reflection coefficient looking into port 1 when the second in a transistor there are only two ports. So, when I say all other ports, I mean multiple port network, N port network. Suppose you have 4 or 5 ports, then all other ports have to be matched except the port 1 where you are looking at the reflection coefficient, that is your S11. But in a transistor there are only two ports, input and output. So, if you match the output port, then S11 is the reflection coefficient looking into the input port, that is all. S21 is like the gain, it is the transmission coefficient, how much are you transmitting from the input to the output side in a transistor. From port 1, which is the input, to port 2, which is the output, how much power or signal are you transmitting when other ports are terminated in a matched load. In this case there is only two ports, so you have to match the appropriate port accordingly, okay, then you get it. So, this is how a vector network analyzer, this is the image of a typical vector network analyzer. I am not advertising for any company here, there are many good companies that sell vector network analyzer. A vector network analyzer is fairly complicated, but the basic premise is that yes, it enables you to measure these S parameters as a function of frequencies, and it also helps you, and that it does that by matching the port that you are going to measure, it will match all other ports so that you can measure the reflected and the incident power, and there are many other things, but we are not going to discuss the instrumentation part of these tools in this course, okay. There is also many tools, pulse tabby setup, load pull, source pull, there are many characterization techniques and tools, a separate course is needed to understand them, but this is a vector network analyzer using which S parameter measurements are done, okay. Now just to give an example or a flavor of how you will find out, for instance, I talked about Z parameter, Y parameter, S parameter. Although you measure S parameter, if you want to practically gain insight about say cutoff frequency, then you cannot just use S parameter, you have to convert from one to another. So, it is not like Z parameters and Y parameters are meaningless, they are very much meaningful. Sometimes and oftentimes you have to convert the measured S parameter into y parameter to do some manipulation, then y parameter to z parameter to h parameter hybrid, and then you plot the cutoff frequency. So, all the parameters are actually useful, because mathematical manipulation and mathematical treatment could be easier on some other matrix, whereas practical measurement is easier on the S matrix, S parameter matrix. This is the reason why all these different matrices are necessary. It just cannot do it one matrix. You cannot just have S parameter, it will make it very complicated. You have to convert the measured S parameters into Y or Z parameter and then reconvert to H parameter in order to gain insight into the cutoff frequencies, for instance. So, now I am showing you an example, a simple example of a Z parameter. Suppose I have this network, it is not a transistor, it is just a resistive network. This is port 1, this is port 2. How will you find out Z11? As I told you, Z11 is nothing but the input voltage by input current when the output is open, I2 equal to 0. If I keep I2 equal to 0, I2 is here, no? If I2 equal to 0, that means this is open, no current is flowing here. Then all the current that you are sending in is flowing here only. So, the V1 by the current that is flowing I1 is nothing but these two resistances. So, that is why it is Z1, ZA plus ZC, that is your Z11. How will you find Z12? Z12 is the input, maybe I can remove this notation. Z12 is basically the input voltage divided by the current from this side when I1 equal to 0, which means this is kept open, this is open. So, there is no current flowing here, there is no I1, there is no current flowing here, but there is some voltage that is dropping. So, what is this voltage dropping divided by what is this current that you are sending in the output side, that ratio is your Z12 when this port is open. So, I can do that as V1 by I2 into V2 by V2 by V2. So, I will do that as V1 by V2 into V2 by I2. So, now V2 by I2, if this by this, it is coming here and there is no current is flowing here. So, V2 by I2 is this, okay, V2 by I2, this quantity is ZB plus ZC, correct. And what is V1 by V2? V1 by V2 is basically the voltage here by voltage here that divides by the ratio. So, that voltage here by voltage there, okay, will divide by the ratio of this is V1 by V2. So, it will be ratio of ZC by ZB plus ZC, because there is no current flowing here. So, there is no voltage dropping on ZA. So, essentially you are dividing ZC by the total of ZB plus ZC, that is your ratio of this ratio. So, if you multiply them together you get ZC. So, Z12 is ZC. So, similarly you can find Z21, Z22 etc. So, this is how you find Z parameter, just to give you an example. Similarly Y parameter, okay, very simple network. I did not talk about ABCD matrix. ABCD matrix is only for 2 port network, only for 2 port network, and it is very easy, in a very convenient in a way that you can actually multiply them together. It is usually useful for a cascade of networks. So, if suppose you have a cascade of different transistors, you can multiply this ABCD matrices together, okay. So, you can multiply one ABCD matrix with another ABCD matrix with another ABCD matrix, and this is what you have here is V1 I1. So, you have the voltage and the current on the input side, V2 I2, voltage and the current on the output side. Remember, on the Z matrix you had V1 V2 on this side, in the admittance matrix you had I1 I2 on this side. So, you have voltage and voltage on input output, current and current on input output, but in ABCD you have voltage and current on the input equal to the ABCD matrix time voltage and current on the output side, okay. So, and this table gives you the basic ABCD parameters for a very simple, suppose I just have an impedance Z in series, then how will the ABCD parameters look like? This is how the ABCD parameters will look like, okay. If I have an admittance in parallel, how will it look like? This is how it will look like. If I have a transmission line of length L with a characteristic impedance of Z0 and a propagation constant of beta, then how will the ABCD parameters look like? They will look like this. It is simple, you can derive this. So, these are the ABCD parameters, and ABCD parameters are very useful for cascaded networks, okay. It is only for 2 port transistors, for instance, and if you have multiple devices, okay, you can multiply them together. Suppose I have a transistor, I have a transistor here which is in series with another transistor and things like that, then this parameter ABCD can be multiplied by other ABCD, and you can keep multiplying them, okay. That is the beauty of ABCD parameters, alright. So, I talked about the vector. Now, for instance, I will take this simple network, okay. So, I will take this simple network. Can you find out the S parameter of this network and the S parameter of this network? I will leave this as a homework because it is again very simple. Remember, in S parameter you do not have to basically keep any port open or short, you have to match the port, Okay, you have to match the port. So you can try to do this as an exercise, maybe I will talk about it in one of the later lectures, but you just give some thought. If I have an S parameter, if I have a network like that, can I find out S11, S12, S21, S22 for this matrix? I have to keep one port matched, neither open nor close, but I have to keep one port matched, and I can assume that there is a 50 ohm characteristic impedance with which I am matching. So can I find out the S parameter? Instead of having these resistance networks, I can even have a transmission line. I can say that a transmission line has a length of L, characteristic impedance of Z0, and a propagation constant of beta. Okay, I can say that there is an incoming wave A0, reflected wave B1, A1 B1. On the output side, the outgoing wave is B2, the incoming incident, you can say the incident wave is A2. Okay. So for this also transmission line also you can go and find out the S parameter. Okay. So keep that in mind, please. Alright. Now we will briefly talk about Smith chart, and Smith chart is a very interesting, helpful and useful concept. This is discussed in very great detail in microwave engineering courses. Here we will discuss it so much as it is necessary for a device engineer to appreciate how an RF device is used actually, or you can say how to build a circuit around an RF device, or how to characterize an RF device, etc. Okay. Many of you watching this video may already be very much familiar with Smith chart, in which case it is basically a recap, but for those of you who have not read or studied or learned about Smith chart, this can be helpful to you. So what is Smith chart? Smith chart is basically, you remember the reflection coefficient gamma that we talked about last class, I think last lecture, we talked about reflection coefficient. You are basically mapping the reflection coefficient on a polar form. Okay, you have an impedance which is typically complex, it's in the form of A plus JB, correct, or X plus JY. That is your impedance. It has a real part, it has an imaginary part, it is a rectangular coordinate. You are converting that into a polar form. You are converting that into a polar form, say gamma into e to the power minus j theta, you can say. Okay. You are converting that into a polar form and you are representing in the Smith chart. So the Smith chart is a polar form representation of these complex impedances. It is easier said than done, but I will explain to you step by step what it means, and I have taken help from a particular YouTube website which I will also list out at the end of this module. But it is there are many YouTube channels, many textbooks, but you can go through them, but the basic understanding is all the same. Okay. So if you talk about a transmission line of say length L, and then there is a load impedance ZL, the line has a characteristic impedance of Z0, there is a reflection that is happening at the load of gamma. Okay. What I do is that all impedances that I will talk about will be normalized to the characteristic impedance of the line. Now typically the characteristic impedance is 50 ohm. That is how you try to you build circuits, you keep the characteristic impedance. When you say I have a device that is matched, you mean usually that you have matched it to 50 ohm line. So 50 ohm is like the universally accepted characteristic impedance. So you try to make everything terminated at a 50 ohm. So 50 ohm is like the holy number, you can say, but anyways in some cases it may be 75 ohm also, it is okay. So I will normalize all the impedances with 50 ohm. So suppose someone tells me I have a line, I have a load impedance or an input impedance or whatever of say 100 minus j25, this is my load impedance, or maybe this is my input impedance or whatever impedance. I will normalize it with the characteristic impedance, and this is 50 ohm. So if I divide it by 50 ohm, it will become 2 minus j 0.5. So that is my normalized impedance. I am going to plot this normalized impedance on a polar form. That is all I am going to do. That is all I am going to do. So 2 minus j 0.5 is a rectangular format. So I have a real part which is 2, and then I have an imaginary part, in this case minus j 0.5. So I will have to come here, maybe this is j minus j, this is plus j, this is real, that is imaginary. So I will come 2 here, and then maybe I will have to come, this is minus 0.5, it is not to scale. Okay. This point is 2 comma minus 0.5. I have come real 2 and then imaginary. Similarly this could be maybe 0.5 and maybe 3. So this could be 0.5 plus j3, something like that. Okay. So it is a real, this is only the real part is what we are going to represent. We do not have, this part is prohibited. This is negative resistance, Negative resistance is not, I mean, not something we are going to talk about here. Okay, negative resistance is the, if you recall, the negative differential resistance and things like that. We are only concerned about positive resistances here. Okay, so I am going to map this region into a polar form, into a circular form. So I have a real on the x axis, I have an imaginary on the y axis. I am going to map this rectangle into this circle. You see this circle? I am going to map into this circle. I am going to convert 2 minus j 0.5 or x plus j y into gamma into e to the power minus j theta maybe. Okay, so this is theta and this is your gamma magnitude. Can you see that? I am going to do that precisely. I am going to do that. Okay, so it's a circular, it's a polar form representation. So what I am going to do now. So I am going to write reflection coefficient. If you remember, this was like ZL minus Z0 divided by ZL plus Z0. If you recall from last to last lecture, this is what we wrote, the reflection coefficient, remember. But I have normalized it with respect to Z0, everything is normalized to Z0. So this ZL by Z0, you know, I will say it is ZL prime minus 1, because I am dividing both numerator and denominator by the Z0, the characteristic impedance, and this is ZL plus ZL dash plus 1. Okay, this is your gamma reflection coefficient. Okay, so this is what I am mapping from this to this. Okay, it will become, the more I speak, the clearer it will become. Okay, the more I speak, the clearer it will become. So suppose what happens is that you have ZL equal to Z0. If ZL equal to Z0, it is a perfectly matched load and your reflection coefficient is 0. This is your 0. Can you see the center? This is your 0. That is your reflection coefficient of 0, and that will correspond to ZL equal to Z0, or in other words ZL prime, because I am talking about normalized impedances, ZL prime is equal to 1. It is equal to Z0 matlab, that is what it means. This is precisely, maybe I will use a blue font so that you know I can make it even more clear, is this point is ZL dash equal to 1 because it is normalized. This point actually is this point. I am converting the rectangular Cartesian into polar, alright, that is what I am doing, this equation I am using. Great. Now suppose I have ZL dash equal to 0, I mean ZL dash equal to 0. In this expression, if I have ZL dash equal to 0, which means the load is 0. What does load equal to 0 mean? It means it is a short circuit, right? It is a short circuit. So if I use ZL equal to 0, ZL dash equal to 0 here, then gamma will become minus 1. Reflection coefficient is minus 1. So this is 0 point, this corresponds to this point. This is ZL dash equal to 0, or the load is short circuit. So this point on the Smith chart is a short circuit point. Okay, I already said that this point is this, correct. Similarly, if ZL dash is infinitely large, which means it is an open load. An open load has an infinitely high resistance, right. Infinity is this, it is not, this is 4, infinity is like the end of the real axis. I cannot plot it, it is the infinite, it is infinite number, that is this. If it is infinity, if this is infinity, then Z dash minus 1 divided by Z dash plus 1 becomes equal to 1. This is the 1 point. So in the circular point, this is 1, this is minus 1 on the real, by the way, this is imaginary j, this is minus imaginary j. This point corresponds to the open load. This point corresponds to the short load, this is the matched load. Can you see that? So this is, I am step by step I am transforming the rectangular plot to the circular plot, alright. Now here is the beauty. Now what I am going to do is that if I fix the real part as 1, suppose I have 1 as the real part, plus I can keep changing the imaginary part. So this is point j5, this is j, this is 2j, 3j, etc. This is, suppose this is minus 0.5j, this is minus j, this is minus 2j, etc. Okay, so I can have 0.5j, I can have 1 minus 0.5j, I can have 1 plus 1j, I can have 1 minus 1j. The real part is constant, but I am changing the imaginary part, which is this line. if I take each and every value of this, they will fall here, 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 here. This will form a circle. You can go and actually check this. You can very much check this. Okay. What I do is that suppose I take 1 plus 0.5j, you have to convert it into gamma. So, it will be, this is z L dash. So, it will be 1 plus 0.5j minus 1 divided by 1 plus 0.5j plus 1. Okay. So, this will become equal to 0.5j divided by 2 plus 0.5j. Alright. Now, you have to convert, you have to multiply numerator and denominator by the conjugate of the denominator. So, you have to convert it into a real part and an imaginary part. Then again you can use 1 plus say 1.5j, again you do this. If you do that math, you will, if you do that math, trust me, you are going to get this circle. So, the straight line in the rectangular Cartesian coordinate where with a fixed real part and a varying imaginary part is actually mapping to this circle here. It is passing through 1 here point. Okay. If I take real part as 2 and I keep changing the imaginary part, the circle becomes smaller. The real part 1 was, sorry, the one was this. Now, if I take real part equal to 3, then it will become this. If I take real part 4, this will become this. At the real part infinity, this is just the point here. You see my point? Now, what if I keep the imaginary part fixed, say j, and I keep changing the real part? That means 1 plus j, 2 plus j, maybe minus 1 plus, oh no, minus 1 cannot exist, say 0.5 plus j. Okay. If I keep the real imaginary part fixed and I keep changing the real part, then how will it look like? How will it look like? This is what I told. This will look like precisely the ones that I am showing you here, which is this line here, these lines here. Those are varying real parts with a fixed imaginary part. Okay. So, for instance, with imaginary part being j, this is the line that you are looking at. With imaginary part being 0.5, this is the line you are looking at. Imaginary part being minus 0.5, you are looking at this line. With real part being fixed is the circle here. See. So, that is how you get the Smith chart. Okay. All the real fixed and varying imaginary, these straight lines are converting to the circles here like that. Okay. And all the fixed imaginary parts with varying real parts are converting to these blue lines here that you saw. Okay. So, that is your Smith chart. That is your, maybe I have a picture, yeah, this is your Smith chart. Okay. The numbers are very tiny to read, but this is the Smith chart that you are looking at. Okay. Now, this is the way the Cartesian coordinates are mapped into real the polar coordinates, and we will see in the subsequent lectures that it makes life very simple when you try to do impedance matching, for instance. It becomes very easier and simple. Okay. So, but for now we will end today's lecture here, where we are ending on the note of Smith chart here. In the next class we are going to talk about more on the Smith chart in terms of the capacitive and the inductive half circles, and maybe we will talk about transmission line and Smith chart and impedance matching. Okay. So, thank you for your time here. I will see you in the next class. Thanks.